Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
Great to be here. We are diving deep today into, well, something fundamental. Compressed air. It's pretty much everywhere in industry.
Absolutely. So our mission today is digging into the engineering trade-offs. We're looking at selecting, sizing air compressors, using our source material as the guide.
Yeah, and we're focusing on let's call them the big three: reciprocating, rotary, and centrifugal compressors. Understanding, why you'd pick one versus another.
Okay, let's start with the basics then. What makes compressed air so useful in the first place?
It's actually quite unique. The energy stored in compressed air can be directly converted to work. You don't need that intermediate step like converting from heat energy first.
Ah, direct energy transfer. That's a neat advantage.
It really is. And looking at the machines that make this happen, one thing that jumped out from the research was the comeback of an old favorite.
You mean the reciprocating compressor?
Exactly. Yeah, for a long time, maybe the late 50s through the mid 70s, the centrifugal type really took over. Higher capacity, less maintenance headache.
Right. The reciprocator sort of fell out of favor.
It did. But then two big things shifted the landscape. Energy costs went way up, and new process plants started getting smaller, more downsized.
And suddenly efficiency became king again.
Precisely. The reciprocator, being a positive displacement machine, just has inherently higher efficiency. So it's clawed its way back into a really prominent role. It's an efficiency play, pure and simple.
Okay, let's start there then. What defines the reciprocating compressor?
Well, fundamentally, it's positive displacement. That means it traps a fixed volume of air and then forces it into a smaller space. It's also intermittent flow, working stroke by stroke.
And its superpower.
Pressure. Definitely pressure. It boasts the widest pressure range of any compressor type. We're talking from vacuum service all the way up to, get this, 40,000 psig.
40,000 psig. Wow. Just to ground that for everyone listening, how does that compare to, say, typical factory air?
Oh, it's orders of magnitude higher. Your standard industrial plant air usually runs somewhere between maybe 100 and 150 psig.
So 40,000 is for really specialized stuff.
Absolutely. Things like polyethylene production, maybe high-pressure gas injection. It just demonstrates the incredible range and, frankly, the robustness of that reciprocating design.
Okay, and that high pressure leads us to staging, right? Why move to two stages instead of just doing it all in one go?
It's really about managing the heat of compression and efficiency too, but heat is critical. A single-stage unit is fine for lower pressures, say 25 to maybe 100 psig.
But beyond that?
Beyond that, the temperature gets really high. So
Yeah.
a two-stage machine compresses partway, then crucially, it cools the air down in an intercooler, removes a lot of that heat. Then it does the final compression stage, usually taking it up to the 100 to 250 psig range.
So the intercooler is key for protecting the machine and for efficiency.
Both, yes. Heat is wasted energy, so removing it improves the overall thermodynamic efficiency significantly. Plus, it prevents overheating components.
And there's a standard that addresses this heat specifically, API 618.
Yes, API 618, that's the big one for heavy-duty recips. It recommends limiting the discharge temperature to 300 degrees Fahrenheit.
300 F. And that's an average.
That's the important part, yes. It's an average. You'll definitely have hot spots inside the cylinder that get hotter than that, so managing that thermal load is vital for the machine's longevity.
Okay, another critical point for reciprocators is oil-free air. Some industries just can't have oil contamination, right? Like food or electronics.
Correct. Zero tolerance for oil. And engineers have basically two main ways to achieve this with the reciprocator.
What's the first method?
Material science. You swap out the traditional lubricated piston rings and packing rings for materials that are inherently low friction or self-lubricating. Think carbon or Teflon-based materials.
And the second path?
Physical separation. This is where you see the crosshead design.
The crosshead. How does that work to keep the oil out?
It uses something called a distance piece. It's essentially a spacer, sometimes a double one, that creates a physical gap, an isolated chamber, between the cylinder where the air is and the crankcase where the lubricating oil lives.
An engineered barrier.
Exactly. Prevents that lube oil from migrating into the compression cylinder.
Got it. And regardless of oil or oil-free, one thing seemed non-negotiable. Inlet filters.
Absolutely mandatory. Think about it pipe scale. Dust from the ambient air. That stuff will just destroy the precision surfaces inside a cylinder bore very quickly. Filters are cheap insurance against catastrophic wear.
Okay, so the reciprocator. High efficiency, amazing pressure range, but maybe more complex with valves and maintenance. What happens when we move to the rotary family? What's the big advantage there?
Simplicity, mainly. The single most important common feature for rotary compressors is they don't have those suction and discharge valves like a recip.
Ah, fewer moving parts to break down.
Exactly. And they also tend to run smoother, less shaking force. That often means simpler, less massive foundations are needed, which is a cost saving right there.
Let's talk about the most common rotary type, the rotary screw, the twin rotor version.
Right. So here you have two precisely machined rotors that mesh together. As they turn, they trap pockets of air, and the volume of those pockets decreases along the length of the rotors, which compresses the air. It's a constant volume, variable pressure machine.
And many of them are oil flooded. You mentioned that.
Yes, that's very common. Oil is injected directly into the compression chamber as it's happening.
Why deliberately mix oil with the air you're compressing? Seems counterintuitive.
It does, but it serves two brilliant purposes. One, it seals the tiny gaps, the clearances between the rotors and the housing. That boosts efficiency. Two, and this is huge, it directly cools the air during compression.
Direct cooling.
Yeah, which means you can achieve really high pressure ratios, like up to 21 to 1 in just a single casing because you're constantly removing that heat. It's a very effective design.
But there's a dry version to the dry screw. What are the trade-offs there?
Well, without the oil for sealing and cooling, they need really precise timing gears to keep the rotors synchronized so they don't crash into each other. And because of those gears and the dry operation, they create a lot of high-frequency noise.
Noise that needs special handling.
It does. You can't just use a simple volume bottle or muffler like you might on a recip. Dry screws usually need a specific, often proprietary silencer from the manufacturer designed to tackle that particular high-frequency pulsation.
Okay, moving through the rotary family, what about the sliding vane compressor?
Okay, picture this. You have a rotor, but it's mounted eccentrically, off-center, inside a cylindrical housing. The rotor has slots, and in these slots are vanes that can slide in and out.
Okay.
As the rotor turns, centrifugal force throws the vanes outward, so they seal against the housing wall. Because the rotor is eccentric, this creates these crescent-shaped pockets of air that get smaller as the rotor rotates.
Compressing the air. Where are these typically used?
They're good general-purpose machines, often use single-stage up to about 50 psig, or maybe staged up to 125 psig. And they're actually excellent for vacuum service, too, down to about 28 inches of mercury.
But the sources mentioned a pretty scary failure mode. Yeah. Vane breakage.
Yes, that's the Achilles heel. Those vanes wear down over time, constantly sliding against the cylinder wall. You have to monitor that wear very closely.
Because if one breaks...
If a vane breaks or wears too short, it can get jammed, or worse, wedge itself between the rotor and the cylinder. That can completely destroy the cylinder. It's a catastrophic, often non-repairable failure. Very expensive.
Yikes. Okay, that makes the next one, the lobe compressor, sound appealing just for its simplicity, even though its compression method is, well, odd.
It is definitely counterintuitive. Lobe compressors don't really compress the air inside the machine at all. They are clearance-type machines, meaning the rotors, which look like figure eights or lobes, just trap air and push it towards the discharge port. The actual compression only happens when that air hits the back pressure already existing in the discharge pipe system.
So the pipe does the compressing, not the machine itself.
Essentially, yes, the rotors are just movers of air volume. Because of this, they are inherently low-pressure devices.
What's the limit, typically?
For larger units, say above 3,000 CFM, the practical upper limit is only about a 10 psi pressure differential. They move bulk air, but not to high pressures.
Interesting. Okay, last one in the rotary group. The liquid ring compressor. Sounds wet.
It is. It uses a rotor to drive a captive ring of liquid, usually water, inside the casing. Again, the rotor is eccentric, so it forms chambers between its blades and the liquid ring. As it rotates, these chambers shrink, compressing the trapped air.
You mentioned the efficiency isn't great.
No, it's relatively low, maybe around 50%, because you're spending energy just slinging that liquid around.
So why use it?
Two key benefits. One, it's inherently oil-free because the liquid acts as the sealant and coolant. Two, and this is often the main reason, it can handle entrained liquids in the incoming airstream, and it actually scrubs particulates out of the air down to micron sizes.
Ah, so if you have really dirty wet air, this is your go-to machine.
Exactly. It cleans as it compresses.
Okay, that covers the rotaries. Now let's shift to the powerhouse, the machine that really dominated for decades in terms of sheer volume, the centrifugal compressor.
Yeah, if you measure by capacity CFM, or just total installed horsepower, centrifugals are king. These are dynamic machines, totally different from positive displacement,
Dynamic meaning.
meaning they use high-speed rotating impellers to fling the air outwards, adding velocity, and then a diffuser section converts that velocity into pressure. They're designed for huge flows, think 1,000 up to maybe 30,000 CFM or even more.
And they seem built for reliability.
Very much so. They're inherently oil-free in the air path. The lubrication system for the bearings and gears is sealed off. The design is relatively simple, dynamically balanced, so they don't need the massive heavy foundations that a big reciprocator would.
And runtime.
Typically very long. You're often looking at 3 years or more between major overhauls, and seeing 6-year runtimes isn't unusual at all. They're built for continuous heavy-duty service.
Given those huge capacities, getting the sizing right must be absolutely critical. The sources highlighted a common pitfall when comparing bids.
This is a big one, yes. You must compare apples to apples. That means specifying the required capacity based on the actual conditions of the compressor inlet, the real inlet pressure, temperature, and relative humidity.
Not just asking for standard cubic feet per minute, SCFM.
Exactly, because different manufacturers might use slightly different definitions of standard conditions, temperature and pressure. If you just ask for SCFM without specifying the inlet conditions, you could end up with a machine that's significantly undersized or oversized for your actual needs. Always anchor it to actual inlet cubic feet per minute, ACFM.
Okay, for quick back-of-the-envelope calculations, there's a rule of thumb for volumetric efficiency.
Yeah, a useful one for plant air systems, around 100 psig. It's typically in the range of 4 to 4.2 SCFM per brake horsepower. For practical estimating, using 4 SCFM per horsepower is usually close enough.
4 SCFM per horsepower. Good to remember. And when designing a new system, you can't just aim for the expected load, right? You need margins.
Absolutely, you need some headroom. The general guideline is, for water-cooled compressors, add about a 30% capacity margin over your calculated system demand.
And for air-cooled,
Bump that up to 40%. Air-cooled machines are more sensitive to ambient temperature swings, so they need a bit more buffer. Now, you can trim these margins back, but only if you have really solid historical data from your specific plant showing exactly what your air usage patterns are. Otherwise, stick to the 30 or 40%.
makes sense. And selecting the right compressor isn't just about flow and pressure. Our sources listed a whole bunch of factors.
Oh yeah, it's a whole system analysis.
Yeah.
You've got to consider, let's see, that air requirements, obviously, the type of driver, electric motor, turbine, the location, any regulations like noise limits, maintenance access and gettability, even things like the subsoil conditions for the foundation.
And costs, too, not just the purchase price.
Right. Power costs, which are huge over the life of the machine, and maybe water availability and cost if you're looking at water-cooled options. It's a complex decision matrix. You might choose a quieter, more expensive machine if you're right next to a residential area, for example.
Okay, speaking of costs, let's wrap up with something that really hit home in the research, the immediate, very real cost of just not maintaining the system properly. Specifically, air leaks.
Ah, yes, the silent killer of efficiency. It's genuinely shocking how much energy is just wasted, bled off into the atmosphere through leaks in pipes, fittings, hoses, tools.
The numbers in the source material were pretty stark.
Yeah.
Using their example cost, about 10 cents per 1,000 cubic feet of air.
Okay, let's take their example. A single leak from just a 3/8 inch diameter opening. That's not huge. You might barely hear it in a noisy plant.
Right, at 100 psig.
That single small leak wastes 6,671,890 cubic feet of compressed air every single month.
Wow, almost 7 million cubic feet, just gone.
And based on that 10 cents per 1,000 cubic feet cost, that translates directly to $667.19 wasted every month from one small leak.
That's incredible. That's more than $20 a day just vanishing.
Exactly. And most plants have dozens, if not hundreds, of leaks like this or smaller. It adds up incredibly fast. It's just pouring money, or rather energy, down the drain.
So the big takeaway there is pretty clear, isn't it?
Absolutely. Before you even think about buying a bigger compressor because you think you don't have enough air, do a thorough leak audit and repair program. Fixing those leaks often pays for itself very quickly and might completely eliminate the need for a larger machine.
Efficiency starts with stopping the waste.
You got it. Seal the system first.
Okay, so as we wrap up, it really brings us back to that central tension we started with, especially now with high energy costs. It's often a choice between, say, the big centrifugal machine, high capacity, maybe lower maintenance, simpler foundation, versus the reciprocator, maybe lower initial capacity per dollar, but that higher inherent efficiency.
It really crystallizes the decision, doesn't it? It's that balance, initial capital cost versus long-term operating cost, mainly driven by energy consumption. And in today's world, energy cost is often the dominant factor over the machine's lifetime. A fascinating engineering trade-off.
A choice between output now and efficiency forever. Lots to think about. Until the next equation, design junkies, we are mechanical engineering made simple.